This idea of statistics, the normal probability distribution. It deals mainly with the idea of normal distribution, where if you were to align or graphically represent your data and it would resemble a bell curve, we will call that a normal distribution. Normal probability distribution is very similar. If we found the probability of all the events in our situation and we compiled them into a graph, the probability would resemble a bell curve if it was normal, meaning that most of our data, the probability of being closer to the mean would be very high, and the probability of being far away from our mean would be very low. And what these numbers at the bottom mean is in the center of our normal distribution, our mean was present, and what these numbers represent are the number of standard deviations away we are from the mean. So if we're in the middle here, we are 0 standard deviations away from the mean. If we go 1 standard deviation away, we are 1 standard deviation away from the mean. And the farther we go away from the mean, the higher the standard deviations go. And the farther for the left, they become negative. Okay? So z-score tells you the number of standard deviations a point is from the mean. So these are all z-score values. So if we have a z-score of +1, that means we are 1 standard deviation to the right of the mean. If we have a z-score of -2.3, that means we are approximately right here. Our data point is right here in our distribution. So negative z-score means we're on the left side of the mean. Positive z-score means we're on the right side of the mean. To find the z-score, you're going to take your data point, subtract the mean, and divide by standard deviation. That will give you your number of standard deviations you are from the mean. If we are calculating probabilities, so this statement saying what's the probability that our data point has a z-score of less than 0. So just looking at our normal probability distribution, we know that the area under this curve equals 1, because if we were to add up all the probabilities, we would add up to 1. So that means the area under this curve would be equal to 1. But if I'm just looking at the probability of our z-score being less than 0, I'm just looking at this portion, which is exactly half of that 1. So if we're talking about half of 1, we're just going to be at 0.5. Sometimes they can get a little more complicated. So say if we were looking for the probability that our data point is less than 1 standard deviation away from the mean, this is when you would use your z-score table. They can be found in your textbook. I'm sure there's plenty of images on the internet and how to read the z-score table. But if you were to look up your z-score table and look at a z-score of 1, the z-score table gives you the area under the curve at your z-score number and gives you the total area from that point and below. So if we're looking for x is below 1, the z-score table gives you right away. So you look up 1.00 on your z-score table, and you should get a value of 0.8413. That means the total area under the curve from 1 and below is about 0.8413, where the total area would be equal to 1. In the event that they're asking for a z-score where they want the area above a number, we're going to use the complement rule, where we can do 1 minus the probability of the z-score value. So the z-table only gives you the area of that z-score and below. So if we want the area of that z-score, and above, you have to do 1 minus the z table value. So in this case, our x is less than 0. We had a area of 0.5, which gave us 0.5, which makes sense because if it's greater than 0, that means we're only talking about the top half of the graph anyway. Similar idea, if we want the probability of our data point having a z-score greater than 1, we're going to use the z-score value of less than 1, and we're going to use this complement idea. We're going to do 1 minus the probability of our data point is less than 1. That gives us a value of 0.1587. Okay, and again, those values were found using the z-score table. There's plenty of videos online about how to use the table and how to read the table. It's just something you got to practice. The whole point of statistics is to make judgments on a population without collecting data on the entire population. So we are going to be taking samples. When we are doing this, we want to try and be as accurate as possible. So we want to remain unbiased. So that means we want to remain true to the population without working with the entire population. In statistics, there are unbiased estimators and there are biased estimators, meaning that if we were to take a sample, there are some variables that will remain true to the population when only working with a sample. And there's some variables that may not remain true to the population based on our sample. The three unbiased estimators are proportion, mean, and variance. So if we took our sample of the population and we looked at these values, these would closely resemble the population parameters. So a sample proportion will closely resemble a population proportion. A sample mean should closely resemble a population mean. A sample variance should closely resemble a population variance. Whereas the median, the range, or standard deviation, they may differ quite a lot from our population. I mean, they might be close, but they also don't have to be close. So when we're thinking about estimators of a population, we want to stick closer to these variables because they closely resemble the population parameters, whereas these may stray a little bit more. This brings us to our next idea of the central limit theorem, which basically says if our sample size is greater than 30, the mean of the population can be approximated using the mean of a sample. So if we took a sample of a normalized population and took the mean, that would closely resemble our population mean. If our population is normalized, our standard deviation can be found by taking the standard deviation of the sample and dividing it by the square root of our sample size. A z-score of our sample can be found by doing your sample mean, subtracting the population mean, and dividing it by the standard deviation. Okay? And again, this only works if the original population is normally distributed or our sample size is greater than 30. So if we have a sample size bigger than 30, we can assume all these are true. And if the population is already normally distributed, we can assume all of those are true.